This is the last podcast for Unit 3 for Chemistry. It's 3.4, and we're going to talk about Hess's law and standard enthalpies of formation. So the first thing we're going to review are the different types of properties that chemicals, substances can have. They're intensive and extensive. Intensive properties are not related to the amount. So no matter how much salt, for example, you have, the density of salt doesn't change. The specific heat of water never changes, whether you have 3 milliliters of it or 300 milliliters of it. All of these things do not change depending on the amount. An extensive property is something that does change. It is related to how much you have. So mass, volume, your heat from your reaction, all of those things are affected by how much you have. And your heat from your reaction, that should make sense because we've been calculating those, and it's based on the mass that you have. So for example, if you had your written formula of this, giving us water, and say our delta H was negative 100 kilojoules, then we would know that this is only for 2 moles of hydrogen, 1 mole of oxygen to form 2 moles of water. If this were only 2 grams, then this value is going to be affected. So extensive properties depend on the amount of the substance that you have. Intensive do not. All right, Hess's law. Hess's law is talking about enthalpy, and we need to remember that enthalpy is a state function. That means it's independent of the path. It doesn't matter how you get there, the change, the delta H will always be the same. So what we're going to do is we can add up equations to come up with a desired final product, and then we can add individual delta H's to calculate the overall delta H. So we'll do some examples with these, but you can take different steps and add up the change in delta H, and you'll get the overall reactions change in enthalpy. So when we're doing this, these are rules and hints you need to remember. If the reaction is reversed, so if the reaction you're dealing with has to run in reverse, the sign for delta H is also reversed. If you change the coefficients in the balanced reaction, just like we were doing before, you also have to change the delta H to correspond with it. So if we multiply all the coefficients by 2, we need to multiply delta H by 2 as well. You want to work backwards from the reaction that you're trying to get, and you're going to use all your individual steps, all your individual reactions to get to that target reaction. So you're going to have your target reaction, which you're trying to get, and you're going to have a list of these other individual steps along the way, and each of those are going to have their own delta H's. And what you're doing is you're trying to manipulate these 4 to give you your overall reaction. And we'll go through an example with this. All right, here's an example that shows you that it's a state function. Enthalpy doesn't matter the pathway you take. You can either do, this is the example taking nitrogen and oxygen and getting nitrogen dioxide. So you can either do a 2-step reaction, which this would be step 1, step 2, or you can do a 1-step reaction where it just goes from here to here. Either way, your change in enthalpy is the same. It doesn't matter how much or how many steps you take, the delta H of your final product will still be the same. So here's our example using Hess's law. 2 forms of carbon are graphite and diamond. Using the enthalpies of combustion for graphite and diamond, calculate delta H for the conversion of graphite to diamond. So the first thing we're going to have to do is we're going to write our individual steps here that we're going to manipulate. This is what we call our target reaction. So when they're talking about combustion, that means that it reacts with oxygen. So when we do this, we're going to take carbon as graphite, and I'm just going to put graphite, plus O2, and that's going to form CO2, and that should look like that makes sense to you. So carbon dioxide. We also have carbon as diamond. reacting with oxygen because it's combusting, and that's giving us CO2. So those are my two combustion reactions, and this is why I wrote those, is because it's telling me that I have a combustion. I can assign my delta H's for these. So my delta H, we'll call this delta H1. For this one they gave me, since that's graphite, is negative 394 kilojoules per mole. And we'll call this delta H2 is negative 396 kilojoules per mole. So when we do this, keeping in mind that that's our target reaction, we need to look, how do we need to manipulate these two equations so that it comes up with that? Well, I take one thing at a time. So the carbon is graphite. I need that to be as a reactant, and it is here. So that tells me I'm going to leave that first reaction as is, and I'm going to rewrite it right here. I'm going to leave it as it is. I'm not going to change anything about it. I don't have to multiply it by anything. It just stays how it is, which means its delta H is also going to stay how it's written. I'm not going to affect it at all. The second one, I need carbon as diamond, but I need it as a product. So here, where it's written as a reactant, I need to reverse this reaction. So I'm going to go CO2, and then I have C as my diamond, plus the oxygen. And since I reversed the reaction, I need to reverse the sign on that delta H. So it looks like this. Okay, just like before, if things are the same on both sides, they cancel. So your CO2s are going to go away, your oxygens are going to go away, you're going to be left with carbon as graphite produces carbon as diamond, which is the target reaction, and that's what we wanted. So then to figure out the delta H for this reaction, all you do is add those up, and you end up with 2 kilojoules per mole. So that tells us also that this is an endothermic reaction, and 2 kilojoules per mole is how much it requires to turn 1 mole of graphite into 1 mole of diamond. Okay, so here's an example that's a little more complicated. They've given us our target reaction right here, and that's what we're trying to calculate the delta H for. We have our 4 different reactions, and these are the ones we're going to manipulate in order to achieve our target reaction. So I'm going to go to this next slide and give myself a little more room. So I've kept the target reaction, and I have my 4 reactions I get to manipulate in order to get that reaction. So when you're doing this, you just want to pick a place. Usually I like to just start on the left-hand side of your target reaction, and then you just work your way over. So I need 2 borons, and they need to be solid, and it needs to be a reactant. So I look down here for that, and I can see it very first, it's right there. It's on the correct side, it's the correct amount, so this first reaction I'm going to keep as is. I'm not going to change anything about it. It has what I need, and it has it on the correct side. And it is important to pay attention to states of matter. They do matter because your delta H's will change based on the states that you have. So that means that since I didn't change that reaction, this delta H value is not going to change either. So there's that. Okay, going to the next one. Finished with you. And finished with you. We have 3 hydrogens, and they need to be gaseous. So I look through here, I'm looking. Here's the only hydrogen that is gaseous, but I need 3 of them. So it's on the correct side, but the quantity is not correct. So what that means is I'm going to take this, and I'm going to multiply it by 3. So when I do that, I also have to multiply my delta H by 3. So rewriting will be 3 H2s, gaseous, plus 3 halves, oxygen, gives me 3 waters, liquid. Delta H will be 3 times negative 286 kilojoules. Okay, finished with that one, finished with that one. The last thing I need is B2H6 gaseous, and that is right here. I need 1 of them, so the quantity is correct, but it's on the wrong side of the reaction. It needs to be a product. So I'm going to flip this reaction around, which means I need to reverse the sign on my delta H. So writing this backwards, I'm going to have B2O3 solid plus 3 waters to give me B2, that is a B, H6 gaseous plus, oh, there should be a plus sign there, 3 O2s. And my delta H for this one is going to be a positive 2035. Okay, but I have this leftover one here, and you might be wondering why in the world is that there? This is here because I'm going to use it to cancel out the waters that I'm going to be left with here, because you can see right here I have 3 waters that are liquid and I have 3 waters that are a gas. Well, those will not cancel because they're different states, and I don't need water in my overall reaction. So the purpose of this fourth reaction is to get the waters to go away. So when I put this in here, I need to make sure that since I need these waters that are liquid to cancel out, that this thing goes as is. I write it down here because I need the liquid water that's in this reaction to cancel with the liquid water that's right here. And I need the gaseous water to cancel with this gaseous water. So I'm going to leave it in the same order that it's in right now, except I need to multiply it by 3 because that's how many I have for the waters down below. So if I multiply that by 3, I need to do the same to the delta H. So this is going to be 3 H2O's liquid yield 3 H2O's gaseous. And then your delta H is going to be 3 times 44. So just to double check that I did a good job here and everything is going to cancel, I look at what needs to go away. Those will cancel with that. My 3 H2O liquids will cancel right there. My 3 H2O gases will cancel with that. My oxygens, this oxygen and this oxygen cancel with my 3 oxygens right there, because that plus that is 3 O's, which will cancel with your 3 O's there. Let's see, I'm looking for anything else. It looks like that is it. So I am left with my 2 boron solids plus 3 hydrogens to give us 1 B2H6. And that matches my target reaction, so I did a good job. And then the last thing I need to do is add up all my delta H's, and the delta H for this reaction then ends up being 36 kilojoules. And that's the final answer for that problem. Okay, standard enthalpies of formation. So enthalpies of formation is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. Here is what standard states is for a thermochemist. This is not the same thing as STP. That is for gases, and this is something completely different. Even though they sound very similar, they're different. So standard states are 1 atmosphere of pressure, 1 molarity or 1 molar if we're dealing with a solution, and 25 degrees Celsius. If you're talking about the standard heats of formation or the heats of the change in enthalpy for the formation of an element, it's always 0. So for example, if we were looking for the delta H heat of formation for oxygen gas, if you tried to look that up, you're going to see that it's equal to 0 because that is elemental oxygen. It is just 0. So you will never find it in the appendix. That's why if you're looking for some of these, they're not there because they're 0. There is a table in Appendix 4 in the back of your book on A19 which has all of these listed. So we need to be able then to write these equations that show that these compounds are forming from their elements. If we take the example of nitrogen dioxide, Nitrogen dioxide is made up of nitrogen and oxygen. So you have to think about, what do nitrogen and oxygen look like in their elemental state? Well, nitrogen is a gas and it's a diatomic gas, so that would be N2. Oxygen is the same, it's a diatomic gas. That would be O2. That's going to give you the NO2 gas. And then you need to balance it. So this would be the reaction for the formation of NO2 from its elements. And then in order to make this go along with the definition that we said, remember when we underlined that word 1 mole, I've got to reduce that to 1 mole. So it's okay to have fractions when I do this. So in order to make that 1, I need to divide everything by 2. And this is really 1. So we're going to end up with 1/2 N2 plus an oxygen to produce a nitrogen dioxide. So this is your correct answer for writing an equation to show the formation of nitrogen dioxide from its elements. If we try another, it's the formation of methanol. Here's methanol's formula. So in methanol, we have carbon, and carbon in its standard state is just carbon solid. Plus, we have hydrogens. Hydrogen is a diatomic gas. And we have oxygen, and oxygen is also a diatomic gas. And that's going to give us CH3OH, and that's a liquid. Methanol is an alcohol, it's a liquid. Okay, so I look to balance, 1 carbon, 1 carbon. I have 4 hydrogens, but my O's are going to get all screwed up, so I'm going to throw a 2 in front of there to make my O's even. That changes my carbons to 2, and then I have 6 plus another 2 is 8, so I have to do 4 there. Okay, this only can be 1 mole though, so we're going to divide everything by 2. So we end up with a carbon plus 2 hydrogens and 1/2 of an oxygen. Oops, there we go. Give us 1 methanol. So there's your equation for the formation of methanol. And if you were to look up methanol in your appendix, you would see that the standard enthalpy of formation for methanol is negative 239 kilojoules per mole. So those are values you can find if they ask you to write a formula for it. Here's what you would do. All right, so since we can manipulate the equations, we can use the heats of formation to figure out the heat of the reaction. And that gives us this rule right here in the middle that's bolded. It says if you take the sum of the heats of formation of the products and you subtract the sum of the heats of formations of the reactants, you're going to get the overall heat of the reaction that you're looking at. And this N right here is the moles, so that's where you would multiply by the coefficient, whatever that is. So you're going to add up all the products, making sure to multiply by the number in front, the coefficient, and you're going to subtract all of your reactants added together, making sure that you multiply also by the coefficients, and that'll give you overall your heat of your reaction. And then remember when we're doing this that their elements that are in standard states won't have a heat of formation because it's 0. Okay, so our example problem here, we're going to use the table on page 247. It's table 6.2 in your book. You don't have to get your book. I will tell you what those values are. But we're going to look for the delta H for this entire reaction using those heats of formations that are given in that table. So the first thing I want to do is I want to list what those are. And remember, if it's an element and it's in its standard state, it's going to be 0. So your oxygen here is going to have a value of 0. We're not going to have to worry about it. It's not going to be included because that's oxygen in its elemental state. The rest of these, though, are going to have a value. So water's value, its heat of formation, is, let's see, negative 1716. And that's kilojoules. And remember we said we have to multiply by the coefficient, so I'm going to take that times 6. Let's see, nitrogen dioxide. I have 4 of them, and I've found nitrogen dioxide. It is 136 kilojoules for its delta H. And then ammonia is going to be 4, and we're going to go times negative 184 kilojoules. All right, so to do this, we want to take the products, add it up, minus the reactants. So products. The product is, and this is at standard states, is going to equal, let's do a square bracket, 4 times 136 plus 6 times negative 1716 minus 4 times negative 184 plus 0. And you don't have to include that plus 0, but you can if you want. And then if you do all that math and you plug it into your calculator, you're going to get negative 1,396 kilojoules. So that would be your answer for that question. You do your products minus your reactants. Okay, the next one, the standard enthalpies of formation. So again, using enthalpies of formation, calculate the standard change in enthalpy for the thermite reaction. You're going to have to look up these values. You probably need to go to the appendix to do that, but again, I will tell you what they are. So we're going to start it the same way we did the other one. We're looking for the overall enthalpy change for the reaction, so we're going to start with the products and then we're going to do the reactants. So our product here is the aluminum oxide. There's only one of them, and I'm going to have square brackets, and its value, if you looked it up, would be negative 1,676 kilojoules. And that's going to be added to 0 because this is elemental iron, so it has a value of 0, and we're going to subtract out the reactants. So the aluminum is 0 because that's elemental aluminum, so 2 times 0 is just 0, plus I have 1 of the iron 3 oxides, and its value is a negative 826 kilojoules. So I really only end up with 2 numbers there, and all I'm going to have to do is plug that into the calculator, and I get a negative 850 kilojoules. So these problems aren't terribly complicated. The time-consuming part of it is just looking up the values in the table. Okay, methanol is often used as a fuel in high-performance engines and race cars. Using the data that we have used before on page 247, we want to compare the standard enthalpy of combustion per gram of methanol with that per gram of gasoline. And then gasoline is actually a mixture of compounds, but assume for this problem that gasoline is pure liquid octane with a formula of C8H18. So the first thing I'm going to want to do is I'm going to end up having to write reactions for both of these. So I'm going to focus on the methanol first because that was given. First, I need to write the formula for the combustion of methanol. So methanol is CH3OH, and it's combusting, and we have a liquid with oxygen, and it's producing CO2 gas and water. So if I balance all of that out, this ends up with a 2, 3, 2, and 4. And then the next thing I need to do is I'm going to do that products minus the reactants by looking up these values. So my products are the carbon dioxide, and I have 2 of them. So 2 times carbon dioxide's value is negative 394 kilojoules. And then I need to add that to my waters. So 4 times waters delta H is negative 286. And then I want to subtract out the reactants. So 2 times negative 239. And remember, it really be plus 0 because oxygen is elemental oxygen, so it doesn't have a heat of formation. You do all of that and you end up with negative 1,932 kilojoules. So that is not really, that's not the final answer, sorry. Ignore that. Your final answer is negative 1,454 kilojoules. And according to the reaction, how we have it written, that is for 2 moles of methanol. CH3OH. So this wanted us in the problem to go per gram of methanol. So all I'm going to have to do is go 1 mole of this, and I'm going to put molar mass on the bottom, and I get negative 22.7 kilojoules per gram of methanol. So that's your first answer for methanol. We're going to do this whole process over again, but this time we're going to do it with the octane. So C8H18 is reacting with oxygen gas again. It's combusting, and it's giving us CO2 and H2O. And when I balance all that out, this ends up as 2, 25, 16, and 18. So I'm going to do the same thing, products minus reactants. Products, I have 16, square bracket, 16 carbon dioxides, and we said that value was a negative 394, using the same value from up here. Plus, I have 18 waters, and that value was a negative 286. Subtract out my reactants. I have 2 of the octanes, and their value is negative 269, plus 0 for the oxygen. So that answer, hopefully, is negative 10,914 kilojoules. And again, that's for every 2 moles of your octane. So 1 mole, and then if you add up octane, it's 114 grams. That way your moles and your moles go away, leaving you in kilojoules per gram. And when you put that into your calculator, you get a negative 47.9 kilojoules per gram. So this is showing you that octane actually releases twice as much energy per gram as compared to methanol. So that's how you do those problems where you have to write out the formula first, do products minus reactants, and then do a little stoichiometry at the end. Okay, the very last slide here is a table. And on this table, we have all sorts of delta H's that you can run across. And I want to quickly talk about what all these delta H's mean. So we're going to go through them. The first one we just finished talking about. It's the standard heat of formation. And that's when we're talking about heats of formation, and that's from the elements that make up that compound. So the delta H for this is the heat of vaporization. Then if we remember, vaporization is when you go from a liquid to a gas. So the energy change that you get from a liquid to a gas, and we know that you have to put energy into the system in order to make this phase change happen. So this is always positive because you're always having to put energy in. It's an endothermic reaction. The heat of condensation is the next one. and that would be the opposite of what we just did there. So the heat of condensation is when we go from a gas back to a liquid. This is an exothermic process. That's actually energy is released. You don't need it, which means that this is always a negative value because this phase change releases energy when it happens. Next thing is the heat of combustion. Okay, the heat of combustion is where you take some sort of fuel, so some CHO or CH, it just depends what it is. You react it with oxygen and you get CO2 and H2O. And when we do that, it's always exothermic. So that means this is always negative. This is always exothermic. It's always releasing energy. So anytime you take something and react it with oxygen, you're combusting it and you're always going to have a negative delta H. This one is showing us a specific example. So this is saying the heat of formation of methane. And so if they're giving you the formula down here, they're talking about the heat of formation of a specific substance. And that can vary. It's going to be positive, negative, it just depends. So when you see the chemical formula down here, they're talking about that specific substance's heat of formation. This one right here is the heat of fusion. And remember, fusion is another word for melting. And when we melt, we go from a solid to a liquid. We know that just like when we vaporize, you have to put energy into the system for this to happen. So this is an endothermic process. It's always positive. The solid right here is the heat of solidification. Fancy word for freezing. So freezing is when we go from a liquid to the solid. It's the opposite of the one we just did. That means it's an exothermic process, and this will always be negative. The sub right here stands for sublimation. So we can cover all sorts of phase changes with these delta H's. So the heat of sublimation is when we go from a solid to a gas. And what you get there, we know that you have to add energy to the system in order to make that happen. So again, this is endothermic, and it's going to always have a positive value. This is the heat of solution. Basically, it's how much or what the energy changes when you dissolve something in water. And we know how that can vary depending on whether it's an endothermic or an exothermic reaction, because we did the hot packs in class, and you can also do the cold packs where it's an endothermic reaction and it pulls heat in from the surroundings. So this one can go either way, it can be endo or exo. Let's see, delta H for the reaction then is the heat of the reaction, and we've used that one before. Heat of the reaction, and we're talking the whole reaction. So not just one part of it, we're talking the whole thing. So these are all the different delta H's that you might come across. Some of them are always endothermic, some of them are always exothermic. Just make sure that you kind of have an idea of what's going on. This one is definitely one of the most common ones, as well as this one. Those are the two you're really going to see the most, but you may see some of these others as well along the way. And that is it. So lots of delta H's, lots of different ways that we can calculate it. We can manipulate the equations to get a target reaction, and we can also do products minus reactants. So make sure you can find all those values in the appendix in the back of your book, because we're going to need those. But besides that, we'll do some practice in class with these. And then later on in the course, we're going to also talk about one more way that we can calculate delta H. So there's a little left with thermal chemistry. We're not quite finished with it yet.